springs. As always, if you enjoy this channel, like and subscribe. So I took this spring out of a clickable pen, and the first thing that you need to know about springs is that they can be stretched and that they can be compressed. And the important thing about this stretch and this compression is the change in spring length. So when a spring is just sitting there, it's considered to be in its equilibrium position, or any position at which we start at where it's at rest. So we could say it starts in this position, and then we stretch it an additional distance. But it's important that we're doing the change in length. So we have to pick an initial position. So for example, here's an unstretched spring. This drawing right here represents a wall or something fixed that the spring is attached to. So this is our initial position that we would call 0 meters. And as we stretch that spring out, it would go to a new position, which would be our x final. And it's that change in position that is x, the change in spring length from equilibrium. Now, you could also hang a spring from the ceiling. So this is our ceiling. And again, we would choose a fixed point while it's in equilibrium to be our initial position x. So what is the definition of equilibrium? This is when a spring is at its rest position, and then we choose a point at the end of the spring to be 0 meters. You could actually choose different points, but the best point to choose is the end of the spring. You could also choose the center of the mass or whatever you put on there. It would be the same result. So let's look at a couple of examples of what this looks like when you apply a force. We have a spring in equilibrium, so its x position is 0, and we hang a mass on it which applies a force and stretches the spring. That's our x final. So what's x, the change in spring length from equilibrium? That's that difference right there. Now, there's another type of problem in which we could hang a mass from the spring and say that this is our equilibrium. So this mass is just at rest hanging there. And if we apply an additional force, we could stretch that mass and pull the spring down further so that our new x, our change in spring length, is going to be the distance between these two initial and final positions. So what is x initial? That's our equilibrium position that we choose somewhere on the spring, or it could be the mass, which we label 0 meters. X final would be our new position, and then x is defined as the change in spring length from equilibrium. So when we look at the formula here on the reference table, it's given as Fs, for force of spring, is equal to k, the spring constant, times x. And if you notice, just like I've been saying, x is the change in spring length from the equilibrium position. So what is Fs? Fs is equal to kx. So that's the force of the spring. K is the spring constant. And x is the change in length from equilibrium. So what is K? K is how stiff the spring is. So if a spring has a very high spring constant, it's going to be very difficult to stretch. And if it has a low spring constant, it's going to be very easy to stretch. So what are the units of the spring constant? Well, we know that force is measured in newtons, and we know that length is measured in meters. So if we divide through meters to the other side, we're left with newtons per meter, the unit of the spring constant. So what does this look like when we graph it? So the force of the spring is equal to kx. And if we rearrange this formula so that k is isolated, we can have our change in y over change in x. So if we put Fs on the y-axis and x on the x-axis, then when we graph this, we get a linear relationship. And what's the slope of the line? The slope is change in y over change in x, fs over x, and that's equal to k. So the slope of the line is k measured in newtons per meter. So let's go ahead and do a problem. Let's say we have a spring, and this is its equilibrium position, and we hang a 20 Newton weight on it, and the question is, find k. So that's going to be Fs is equal to kx. The force applied to the spring in its new position is going to be 20 newtons. And we're going to divide that by what? Well, is it 0.2 or is it 0.3? It's neither. It's the change. And that change is going to be 0.1, the difference. So we divide through 20 by 0.1 and we get 200 newtons per meter. Gravitation. So what is gravity? A very basic definition is the force of attraction between any two objects due to their mass. So note that it has to be two objects. The gravitational force only occurs when one object pulls on another. So, for example, we tend to think of gravity as something that Earth has. Earth has a gravitational field, but the force of gravity due to the Earth has to be on an object. So, the Earth exerts a force of gravity on a person, and that force of gravity is towards the Earth. But you can't have this force without an equal and opposite force. So while the Earth pulls on the person, the person pulls on the Earth with exactly the same amount of force. Now, that's not to say if a person fell towards the Earth that they would have the same acceleration, but the force has to be exactly the same. So we have a force of gravity on both of them, equal and opposite. Now, we have a name for the force of gravity when we say it's acting on an object towards the Earth. We call that the weight. And that's why we've been using the formula Fg equals mg and been calling that the weight. But it's also the force of gravity. Now, if we have a proton and an electron, we know that there's a force due to electrostatics. This is called a Coulomb force, and we haven't learned about this yet, but I just want to discuss this because this is going to come up multiple times in this course later on. So we have a gravitational or an electrostatic force of attraction, this Coulomb force, but we also have a gravitational force. So when we have objects, it's possible to have more than one force. Now, in this case, the electrostatic force is much larger than the gravitational force. So the net force would be the sum of these two. But this force is so weak compared to this, it's basically negligible. We could actually ignore it. Okay, so what's the formula? The formula is big G, M1, M2, so these are the two masses, and R is how far they are from each other. And that distance is from center to center of the object. Now, if there's two forces, why is there only one force in the formula? There's only one force here because the force happens to be the same because it's an equal and opposite force. Now let's look more closely at R. M is kind of easy, that's just the mass of the objects, but R is not necessarily the radius. In fact, in most cases, it is not the radius, and you'll see why we use R in just a minute. But this R is the distance from center to center. Between any two objects. Now that's important to remember. So why do we use the letter R? Well, the reason is because very frequently we solve for the force of gravity of an object on the surface of a planet. So how far from the center of the Earth to the center of this person? How far away are those? That distance is center to center r, which also happens to be equal to the radius. So it's better to think of this r as distance between centers rather than thinking of it as the radius. Okay, what's this big G all about? This is the universal gravitational constant. Now, all that means is that anywhere in the universe, there's a number that helps us to figure out the exact force of gravity. Now, this number is actually extremely, extremely small. It is 6.67 times 10 to the minus 11. So that's 0.000010667. That tells us something. It tells us that the force of gravity is extremely small. So where is this number on your reference table? Well, it's actually the very first one. It's right here, universal gravitational constant. The unit's Newton meter squared per kilogram squared. M1 is easy, that's your mass. And then the other mass is just mass 2. And R we're defining as distance between centers. And obviously Fg is the force due to gravity. And let's look at the units for a second. So we have Newton meter squared per kilogram squared. Here we have kilograms times kilograms over meters, but it's squared, so that's going to be meters squared. So kilograms, kilograms, those are going to cancel with the kilogram squared. Meter squared, that's going to cancel with the meter squared, and we're just left with newtons, the unit of force. Let's do a problem. Let's say we have the Earth and we have the moon. And the question is, what's the force of gravitational attraction between the Earth and the moon? Well, we need to know some stuff to get this problem started. So where are you going to find the mass of the Earth? Well, it's on the reference table. Mass of Earth, 5.98 times 10 to the 24th. Also, the mass of the moon is here, 7.35 times 10 to the 22nd. And then we need to know the distance between them, not the radius, not the radius. We need the mean distance from the Earth to the moon. Mean just means average because the path of the moon around the Earth is not a perfect circle. It's actually slightly elliptical, so we have to use the average distance. So we have our masses and we have our distance, and we're just going to go ahead and do our formula. And now we just need to put the numbers in. So we have 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared times 5.98 times 10 to the 24th kilograms times 7.35 times 10 to the 22nd kilograms, all divided by 3.84 times 10 to the 8th meters, all squared. One of the most difficult parts of solving these problems is actually making sure you're using your calculator properly. So if you want to do this in one step, you have to make sure that you put parentheses around this entire top before you do the division of this number squared. Now, if you feel like you really want to go slowly and make sure you don't make a mistake, you can multiply these across, write that number down, then divide by this number squared. So I'm going to show you both ways to do it. Now, there's one other important thing. Many physics students put this into their calculator as times 10 caret negative 11. The problem with that is it treats this as two different numbers. It treats this as 6.67 multiplying by 10 to the power negative 11th. But there's an E key on your calculator that lets you treat this as a single number. And the reason that this is good is because if you multiply these across and you divide by a number, the last thing that you put into the calculator was this, and that will be the only thing that gets divided. So it's much better to use the E key. Now, the E key on your calculator might look like this as an exponent key, or it might be a double E like this. And I'm going to show this to you on probably the most common calculator that people use. So I'm going to clear this, and I'm going to do 6.67, then I'm going to hit my second E key, double E, and it shows up as 1E, negative 11th, times 5.98, second E key, 24, times 7.35, second E key, 22. And I'm going to multiply that through. So now I have 2.93 times 10 to the 37th. And then on the bottom, I'm going to do 3.84 second E key, 8. And again, if we did the times 10 to the method, we would need brackets around that. But because we have an E key, it is automatically treating that as one number, so that when we square it, it's not just squaring the power, it's squaring the entire number. 1.47 times 10 to the 17th. And then if we divide those two numbers, we end up with 1.99 times 10 to the 20th newtons. So we have to be a little bit careful here. There's only one force. This is the force of the Earth on the moon, and the moon is going to receive a force this way, but it's also the force of the moon on the Earth, and that's in this direction. One force, equal and opposite forces. So if you had wanted to go through and do this all at one step, then you need to put a parentheses and do exactly what we just did. Close the parentheses, then divide by this number squared, and always using your double E key. Let's look at what this looks like in a graph. So before we start to put some numbers in, let's just look at the force of gravity near a planet, and we'll just pick Earth. As we move further away from the Earth, we would expect an astronaut to weigh less and less. The force of gravity as you get further apart gets less. But how does it get less? Well, the way that it gets less is by an inverse square law. So big G is not changing. The mass of the Earth is not changing. The mass of the person is not changing. The only thing that's changing is r squared. So we can change this equal sign to a directly proportional to. So F is directly proportional to 1 over r squared. So what happens to the force when we change r? So we're going to start out here where the person is at 1r. So at 1r, that's just going to be their weight. Okay, I'm going to say, we'll do this right after, but let's just say the astronaut is 800 newtons. Okay, it's an 800 newton astronaut, and they're at 1r, so they are going to have a value of, we'll just call 1, or we could say 800 newtons. So we have 1 over 2r squared. This gives us 1/4, because we're squaring the r and the 2, and 0.25 fg. And as we move further out, we have 1 over 3 squared, which is a ninth, 0.11. 1 over 4 squared, 16th, 0.06. 1 over 5r squared, 0.04 fg. And so we end up seeing this inverse square relationship. with an asymptote, which means that this is never actually going to reach 0. So again, the weight of the astronaut, each time we move up, it decreases by 1 over r squared. So here are some popular questions that get asked on physics exams. What happens to the weight if we double the mass? Well, just mass 1. So if we double mass 1, we put a 2 in here. The only thing we've changed on this side of the equation is a 2 in the top, so that becomes double. So that's double F. What happens if we double mass 1 and triple mass 2? So if we put a 2 in here and a 3 in here, that would be 6F. What if we double r? Well, we saw that in the previous problem. If we double r, that's double r squared, and it's in the bottom, so that becomes a 4th, or F over 4. So what happens if we double mass 2 and we triple r? So in that case, we're doubling m2, so we're putting a 2 up here, and we're squaring that 3, so that becomes 2/9, and 2/9 is, that's it, 2/9. Okay, and what happens if we reduce 1r to 1/4 r? Now, this one is tricky. The first thing to think about is we're moving closer together. If we're moving closer together, the force is going to go up. Sorry, the force is going to go, it's going to go up because we're getting closer to the planet. So if we reduce this to 1/4, what are we doing? Well, we're squaring that, so that becomes 1/16. So we have 1/16. But to get this through out of this bottom here, we're going to multiply through by 16 over 16. So these will cancel out, so the force will go up by 16. And that makes sense because we're getting closer together. Okay, this is a little bit more of an honors or advanced idea. What if we wanted to find the strength of the gravitational field around an object? Let's do this for the Earth. So if we have the weight of a person, so we could say the mass of a person in a gravitational field, then we would have the mass of the Earth of the gravitational field, the mass of the person, divided by r. In this case, distance from the person to the surface of the Earth would be the radius squared. And then we see that we have the mass of the person on both sides of the equation. So this gives us G equals big G, mass of the Earth, over r squared. So what this tells us is how strong the gravitational field is at the surface of the Earth. We could also use this to find the gravitational field of any mass at any position. And if we did this specifically for the radius of the Earth and the mass of the Earth, that number would come out to 9.8 meters per second squared. So one last thing, we did this in one of the other units and earlier in forces, but it's important in this unit. What if they ask you for the strength of the gravitational field on a planet? Okay, could be Earth, but could be some planet Q or X or something like that. If we divide through mass on the other side, we have Fg over m. And this is a direct relationship. Change in y over change in x, change in y over change in x. So our slope is G, the strength of the gravitational field, in meters per second squared. So if they ask you for the strength of the gravitational field on a planet, and they give you a graph like this, all they're asking you to do is to find the slope.